Let's learn about the definition of a linear transformation. A function t from Rm to Rn is called a linear transformation from Rm to Rn if for all vectors u and v in the domain Rm of the function and all constants c, you can compute t of u plus v simply by taking t of u and adding to it t of v. And similarly, you can compute t of a constant c times u as the constant times t of u. For example, if you knew that t of the vector 1, 2 is equal to 3, 4, then if t was a linear transformation, you could conclude that t of 2 times 1, 2 is equal to 2 times t of 1, 2. And since we already know what t of 1, 2 is, so that's going to be 2 times t of 1, 2 is 3, 4. And so that would then equal the vector 6, 8. And here we have this is t of the vector 2 times 1, 2, so 2, 4. So if we knew that the vector 1, 2 is mapped to the vector 3, 4, then we would automatically be able to conclude that the vector 2, 4 is mapped to the vector 6, 8. Here's another example. Let t be the transformation given by t of xy is equal to this matrix 1, 1, 2, 1 times the vector xy. So what does that really mean for t? T of xy is then given by this matrix multiplication. So let's do this out. The matrix 1, 1, 2, 1 times xy means I'm taking 1 times x and adding to it 1 times y for the first coordinate, and 2 times x plus 1 times y for the second coordinate. So that equals the vector x plus y in the first coordinate and 2x plus y in the second coordinate. Let's verify with some examples that this is indeed a linear transformation. Let's say u is the vector 1, 1, and v is the vector 2, 1. Then I have that t of u is equal to, I need to add up with both components of u, so 1 plus 1, and the second one is 2 plus 1. So that's the vector 2, 3. And t of v is equal to, again, the sum of the two components is 2 plus 1, and 2 times 2 is 4 plus 1. So t of v is equal to 3, 5. And so therefore, if I add those two up, I have that t of u plus t of v is equal to the vector 2, 3 plus the vector 3, 5. And that equals the vector 5, 8. Now the claim is that I get the same thing when I add up u plus v first and then apply t to it. So let's find out what u plus v actually equals. U plus v equals 1 plus 2, that's 3, and 1 plus 1, which is 2. So that t of u plus v is equal to, for the top coordinate, I need to add up the two components. 3 plus 2 equals 5. And for the bottom, I need 2 times the x component, so 2 times 3 is 6 plus 2, which equals 8. So the vector becomes 5 and 8. And indeed, those two are the same. Let's look at this example. T of xy is given by 2x plus y plus 1 for the first component and x plus y for the second component. Is t a linear transformation? Let's find out. Let's plug in two vectors. Suppose u is the vector 1, 0 and v is the vector 0, 1. Then t of u is equal to 2 times the x component, so 2 plus 0 plus 1. And for the bottom component, I simply add up x and y, so I get a 1. So that is 3, 1. Whereas t of v is equal to 2 times 0, which is 0, plus 1, plus 1. And for the bottom component, x plus y, that's also 1. So that equals 2, 1. When I add those two up, I get t of u plus t of v, which equals 3, 1 plus 2, 1. So that's the vector 5, 2. On the other hand, u plus v is the vector 1, 1. And so t of u plus v, I now have 1 for x and 1 for y. So 2 times x, that's 2. Y is also equal to 1, so plus 1 plus 1. At the bottom I have x plus y, which is 1 plus 1, so that's 2. So overall, this is the vector 4, 2. That's not the same as the vector 5, 2. The problem here really was in the plus 1 right there, but we'll learn about that a little bit later. Now how about t of u minus v? Our definition had said that t of u plus v has to equal t of u plus t of v. How about t of u minus v? Is it the case that t of u minus v is equal to t of u minus t of v? Well, that is indeed the case, and I'll indicate to you how you would show that, and we'll learn more about properties of linear transformations in the next videos. Here's one way of looking at this. How about t of u minus v? One way of rewriting that would be as t of u plus minus 1 times v. So at a plus sign, namely this plus sign right here, I can pull a linear transformation apart. So if t is linear, then that equals t of u plus t of minus 1 times v. But t of minus 1 times v is a t of a constant times v, and we know that constants can go to the side for a linear transformation. So this then equals t of u plus minus 1 times t of v, and another way of writing that would be t of u minus t of v. So it is indeed the case that t of u minus v equals t of u minus t of v, and we'll learn more properties of linear transformations in the next videos.